Thank you. So the motivation for this work is to come up with an understanding of different type of metals that you can use for hot contact microelectromechanical switches. And the idea is to not only look at different type of metals, but also understand how different parameters like their density, melting point, stiction force or adhesion force at the surface, Casimir and van der Waal, play a role. So we have been working in this problem for a long time, since 2000, 2001, 2002. And the idea is to come up with a mechanical computer. And where would you use something like that? Maybe in environments where you have large doses of ionizing radiation, space applications, and also inside nuclear reactors. And we have basically exhausted most of the metals that people have thought that would be good candidate for these switches. So the idea was to kind of step back and try to understand the science of it. So if you look at mechanical switches, they offer you kind of multifunctionality. In that, by that I mean, if you have a MOSFET, let's say, you can use it as on and off switch. But if you have a mechanical structure, you can pattern different metal traces on it, and with one device you can have AND gate, OR gate, XOR gate, stuff like that. So that way you can reduce the number of movable parts and improve their lifetime. And we have like 1-bit adder that is completely integrated on the same diaphragm, and when it goes up and down, it performs the computation for you. So in this particular work, we have limited the number of cycles that we have used to 100,000. Of course, this is not enough. You need to be able to project up to maybe 1 billion cycle. But the idea was that we will perform very sensitive current measurements and try to understand from these exquisite measurements whether things are going to be any different or how they are going to evolve when you go to large number of cycles. So 100,000 is not enough. You really need to be able to project to maybe 1 billion cycles. But the idea is that if you perform very sensitive current measurements, you may be able to predict what's going to happen later on. So in our measurements, we kind of use different type of metals on an AFM, dedicated AFM system with a tip that came down and then touched the surface, and then performed IV measurements, and we control the environment that was sitting. Our previous work showed that there are large number of, there is a large variation in lots of different type of metals. In that previous study that we reported in 2013, we went up to about 1 million cycle. And you can see the kind of changes that you see. This is the contact resistance, and this is the IV characteristics of these switch type structures. And you can see that there is a large variation in the stiction force, which kind of determines the clamp down. So this, you're turning it on, and then when you go back, it turns off at different voltage. And this hysteresis is caused by the stiction force at the surface. If you look at the literature, there are some other work that people have reported the contact reliability. But if you look at the way the variations are, they are not very finely measured current, so the current noise and stuff are not captured, and we are trying to capture that. So this is what I exactly mean. So if you go to large number of cycles, and if you have a fine measurement of the current, you can see these variations as a function of number of cycle, and by analyzing these variations, you may be able to understand what's happening to the contact. So this shows the experimental setup. There is a plexiglass environment where we can change the gases. Nitrogen was used in most of our experiments. And this is the dedicated AFM system, very simple AFM system that we used for these IV measurements. So if you look at the average variation in the current, most metals are okay. Metals that have native oxides on them, things like tungsten, they show these very weird behavior, and I'm going to talk about this weird behavior, why it goes up and sometimes goes down in terms of the anodic oxidation at the surface of these metals and their breakdown over subsequent IV measurements. So there are maybe 5 or 6 active groups in this area in the United States, And all sorts of results are reported, and a couple of groups use tungsten, and this work basically shows why they are observing what they are observing. So if you look at the current versus voltage very carefully in tungsten, you can see that this is kind of relatively large voltage in overall scheme of things. But if you look at the forward bias and the reverse bias, this is a typical measurement. You can see that when you're moving forward, at some point you start getting this noise in the current, and as you keep pushing it, then it may completely turn on, and then when you're going back, you don't see the same noise in the reverse direction. So this noise-like behavior is really created by these white spots that you see on the AFM scan, where the tip comes down, platinum tip comes down and contacts the tungsten. And then in this cycle of the operation, you're growing anodic oxide. And if you kind of go back in the reverse direction, you can break it down. Now that oxide can be broken down as you start increasing the voltage. So you increase the voltage between the tip and the sample, start growing anodic oxide. So that's when the current goes down and you see all these noise-like behavior. And then as you keep the voltage to higher values, you break down the oxide that you have grown, and then you get the rest of the cycle. Another thing that comes up, so that we have seen in tungsten and a couple of other metals, but in tungsten it is really pronounced. So one has to be careful about the anodic oxidation growth and subsequent breakdown. Another interesting thing that we have observed was that when we take the platinum tips that we use for our IV measurements and then look at the SEM image of those before and after, you can see that there is this growth of material around the tungsten tip. And now the question is, what is that material and where is it coming from? So in order to understand that, we looked at this contacting process a little bit more carefully, and you can see that if the tip is energized, you apply some voltage, let's say 0.5 volt or so, and then as the AFM tip comes down and touches the sample, the tungsten sample, you can get this micro, or in this case really nano plasma generation between the tip and the sample. And this plasma can cause activation of or synthesis of lots of different type of carbonous materials. So CO2 is everywhere. There's water, moisture layer on the surface of the tungsten, and the combination of the spark and CO2 and moisture can start coating this with polymers. And that's what we have observed. And you can also look at the thermal image of the tip approaching the sample, and then you can see that it heats up when it touches. So the contact area is very small. It's about 4 nanometer squared type of thing, and even at very small voltages and current levels, you can generate quite a bit of heat there. So the next thing that we wanted to understand is the relationship between contact reliability and adhesion forces, or the surface adhesion forces in these different type of metals. So so this is an example of a nanoelectric mechanical switch that my group did quite a bit ago, maybe about 6 years ago, and you can see the IV is very clean, but this hysteresis is caused by the adhesion between these two cantilever beams that are vertical, and this was formed with focused ion beam. And in some applications, this is good because it gives you essentially a jitter-free type of switching. Hysteresis in some applications are good. But in most applications, you want to eliminate this memory effect and go up and then come down. So that is one motivation. The second motivation is that we know that metals or surfaces that have large adhesion forces, they may start attracting particulates and then cause reliability issues. So a very quick reminder of or refresher on the Casimir force. It is basically caused by excluding electromagnetic fields between two surfaces, and this is a simple equation that tells you it is kind of proportional to the plasma frequency, which is sigma over epsilon type of has dependence. So larger conductivity surfaces usually have larger Casimir forces. And the way we measure it is we bring down the AFM probe, touch it, and then look at the force versus displacement curve shown in here. So when you bring this down, this is the displacement caused by bringing down the probe, or you keep the probe fixed and the sample goes up. And then at some point there is a contact between the tip and the sample, so the force versus displacement curve goes up. And then when you try to retrieve this, bring down the sample, the tip is fixed on its shank. Then because of the stiction, it kind of sticks to the surface till you have to exceed certain distance, and then it kind of snaps back. And so this force is adhesion force that we measure. And for this we use different AFM probe system, which is much more sensitive than the one that we use for the IV. So this table shows the stiction forces that we measured on a variety of different metals. And you can see that there are anywhere between 30 to 90 or so nanonewton. So there are no surprises in there. Ruthenium is something that is used in contacts for a long time. It is corrosion resistant, and you can see that its Young's modulus is pretty large, and its adhesion force at the surface is 55. So we have looked at that a little bit more carefully. But if you look at these typical metals that we use, you can see how the stiction force changes in them. So platinum, our tip was platinum, so it is well known from Casimir analysis that similar materials, similar metals will have will show large stiction forces or Casimir forces. Next is ruthenium, then nickel, tungsten, and then iridium. Tungsten and nickel have anodic oxidation problem that I mentioned, and some of these metals are also catalytic. So this problem that I mentioned, that you have this microplasma and then there is water moisture on your sample and then CO2, some of these metals, they catalyze that into polymers more than the other ones. So what I want to do now is to ask myself if metals have these problems, and larger stiction force means larger particulate generation and attraction to surface, with kind of cause lots of reliability problem. What other materials one can use? And 2D materials have become of interest. And two-dimensional materials have the added advantage that, for example, if you look at graphene, graphene has this closed packed carbon layer, and how much energy does it take to pluck one of those carbon atoms out? And if it is relatively high, then these would be good contact materials because they're completely closed packed, highly packed and closed structures. There are no dangling bonds essentially, other than the hybrid pi bonds that are not really dangling, but they can cause problem later on, but they're much better than what you get on metals. So this kind of shows you tungsten diselenide, molybdenum disulfide, the typical 2D materials that you can get these days, graphene. These are all experimental data. We didn't kind of put this in our extended abstract, but these are some new results that I decided to include in this talk. 2D materials give us very good, some very good performances. So graphene is what is used by everyone, but looks like the tungsten disulfide, diselenide may be better. So going back to the graphene problem, and we are repeating this with all our 2D materials, the question is how much energy in terms of EV takes to pluck atoms from the surface of these 2D materials. Now, that's a simple question, but the answer is very complex. It depends on what you have on the surface. These are done in laboratory environments, so you can end up with water vapor in there. And if you happen to clean your sample with methanol or other type of alcohols, you may have residues in there, and those all affect the energies that you measure. So depending on what you have, these are all color-coded, you can either end up with holes, that's shown in here. So the platinum tip comes down and then touches the surface. You apply a certain amount of voltage and pull back the tip, and then the idea is to create a hole in there. And depending on the surface conditions, you can either end up with a hole or some kind of a hill, since graphene layers can adjust themselves. So if you have the right environment on the surface, you can cause both these holes as well as hills. And in some cases, you rearrange the atoms and you end up with a situation like this. But no matter what, there is no anionic oxidation, so this is much better than tungsten. And since this closed back structure, it may give you higher reliability. That is something that we are continuing. So in summary, I kind of looked at contact resistance evolution and showed that in some cases you get anionic oxidation and its subsequent breakdown, and that can give rise to noise in the current and reliability issues in the contact material. And sparking or microplasma in combination with stuff that we have around the material can cause polymeric growth on your electrodes. And I looked at surface adhesion forces in some materials and kind of thought about some of the thoughts we have that surface adhesion force can cause problem, both in terms of hysteresis as well as attracting particulates near the contact. So with that, I'm done. If you have any questions, I'll be more than happy to answer. Thank you.